Hello everyone, my name is Vardhan. My registration number is 13BC 454 and I am doing assignment on programming language translator given by our professor Kannada Sanar. So the question is, explain with example the following code optimization techniques. So the first one is common sub expression elimination, the second one is copy propagation, the third one is dead code elimination, and the fourth one is code motion. So first of all, we are going to see common sub-expression elimination. In the compiler theory, common sub-expression elimination (CSE) is a compiler optimization that search for instances of identical expressions. That is, they all evaluate to the same value and analyzes whether it is worthwhile replacing them with a single variable holding the computed value. So in the following code, A equal to B multiplication with C plus G and D equal to B multiplication C multiplication E. So it may be worth transforming the code to temp equal to B multiplication C, A equal to temp plus G and D equal to temp multiplication E. So here we can see that B multiplication C is a sub-expression that is used in two different sub-expressions. So we can calculate B multiplication C and we can store it in a temporary variable, and we can use temp in two different expressions having B multiplication C. So what are the benefits of using common sub-expression elimination? So the benefits of performing CSE are great enough that it is commonly used optimization technique. In simple cases like in the example above, programmers may manually eliminate the duplicate expressions while writing the code. The greatest source of CSEs are intermediate code sequences that are generated by the compiler, such as for arrays indexing calculations where it is not possible for the developer to manually intervene. In some cases, language features may create many duplicate expressions. For instance, C macros where macro expansions may result in common sub-expressions not apparent in the original source code. So the next one is copy propagation. So in the compiler theory, copy propagation is the process of replacing the occurrences of targets of direct assignments with their values. A direct assignment is an instruction of the form x equal to y, which simply assigns the value of y to x. So from the following code, y equal to x and z equal to 3 plus y. The copy propagation would yield z equal to 3 plus x. So we can see that if we are using a y in a different expression, then we can use the value of y instead of writing y. So the copy propagation of the following code will yield to z equal to 3 plus x. So the copy propagation often makes use of reaching definitions, usedef chains and def-use chains when computing which occurrences of the target may be safely replaced. If all upward exposed uses of the targets may be safely modified, the assignment operator may be eliminated. Copy propagation is a useful cleanup optimization frequently used after other optimizations have already been run. Some optimizations, such as elimination of common sub-expressions, require that copy propagations may be run afterwards in order to achieve the increase in the efficiency. So the next optimization technique is dead code elimination. In compiler theory, dead code eliminations, also known as DCE, also known as dead code removal or dead code stripping or dead code strip, is a compiler optimization technique to remove code which does not affect the program results. Removing such code has several benefits. First of all, it will shrink the program size. Second, an important consideration in some contexts, it will allow the running program to avoid executing irrelevant operations, which will reduce its running time. It can also enable further optimizations by simplifying the program structure. Dead code includes code that can never be executed, that is called unreachable codes, and code that only affect the dead variables, written to but never read again, that is irrelevant to the program. So we can take the example of a foo function. So here int a equal to 24, int b equal to 25, int c equal to a left shift by 2 and return c, and b equal to 24, and after that return 0. So here we can see that b and b equal to 25, that is assignment to a dead variable since b is not used in the program. Hence, removing int b equal to 24 will make program efficient. Again, we can see that any statements that are written after return cannot be executed. Hence, they are unreachable code. Hence, removing the unreachable code will also make the program efficient. Hence, b equal to 24 after return c and int b equal to 25, both are dead code, and hence they should be removed for optimization. So the next optimization technique is code motion. So in computer programming, loop invariant code consists of statements or expressions in an imperative programming language which can be moved outside of the body of a loop without affecting the semantics of the program. Loop invariant code motion, which is also called hoisting or scalar promotion, is a compiler optimization technique which performs this movement automatically. For example, for int I equal to 0, I less than n and I plus plus, inside for loop we are writing x equal to y plus z and a of I equal to 6 star I plus x star x. So the calculation of x equal to y plus z and x star x can be moved outside of the loop since within they are loop invariant code. So the optimized code will be something like this: x equal to y plus z and t1 equal to x star x, and in after that there will be for loop. For int I equal to 0, I less than n, I plus plus, inside for loop there is ai equal to 6 star I plus t1. So what are the benefits of the code motion? So first of all, loop invariant code which has been hosted out of the loop is executed less often, providing a speed up. Another effect of this transformation is allowing constants to be stored in a register and not having to calculate the address and access the memory or cache line at each iteration. However, if too many variables are created, there will be high register pressure, especially on processors with few registers like 32-bit cross 686. If the compiler runs out of the register, some of the variables will be spilled. To counteract this, the inverse optimization can be performed, that is called rematerialization. Thank you very much.